Hello, everyone. My name is Leo. I'm thrilled to have this opportunity to introduce myself. I live in Shatin. I have three family members, my wife, my son, and myself. I graduated with the first degree in applied chemistry in Hong Kong Baptist University in 1996. I've got my PhD degree in chemistry in the Hong Kong Chinese University in 2001. I have a passion for chemistry, and all my past working experiences are surrounding chemistry. It includes my tutorial experiences during my time in Hong Kong Chinese University and my private lessons during my time studying in the Hong Kong Baptist University. I'm a chemist. I have over 20 years working experiences, working in companies of different nature. I've started my first job working in a wastewater treatment plant in 2000. Then I've entered into another sector, the consumer product testing industry, working in some international testing laboratories. I'm involved in chemical testing development, chemical product testing, and technical services. In addition to chemical management, I've also explored and experienced in operation management, business development, and general management. In my last job, I've been working in a fashion brand for sustainable chemical management in the supply chain. It can leverage and gauge the chemical safety in apparels and footwear products. In my leisure time, I love hiking, cycling, and jogging. I can enjoy the lovely scenes during the exercise. I even challenge myself with some difficult trails. I may also plan to explore hiking in other countries, such as the Indonesia, because I'm attracted by the scenes and the routes there. I also like some sports games, such as the badminton, tennis, and pickleball. I also enjoy playing indoor activities with my family members. It includes the board games, building Lego models, table tennis, and snooker. It can further bond the relationship within the family. I consider myself curious and detail oriented, with a methodical approach to learning and connecting them to the real world applications. I'm sociable as I like to exchange my ideas and experiences with my friend for continuous development and learning. Looking ahead, I'm, I aims to continue use my expertise in chemistry in my upcoming job. I'm applying for the part-time positions at the Candlelight Education Center as I wish to contribute to the field of education using my expertise in chemistry. Recently, I've observed situations that many children are dependent on the tutorial lessons to improve the academic results or meet their targets. This situation triggers me to have this move. I'm thinking whether the job of education is suitable for me. That's why I'm applying for the part-time positions. That's the end of my self-introductions. For the next part, I will do the demo lesson. Hey class, today the topic of our lessons is the reasons for the transitions element complex are color. The factors affect the color. Before the lessons, I have a couple of questions for the class. Where is the transitions element in the periodic table? Anyone try? Yes, Peter. Yes, correct. They're located at the middle of the periodic table, the d block element. You're correct. Why they call the d block element? Joey? Yes? Yes, correct. They have the partially filled d electrons. How the d electron relates to the color of the complex? Anyone try? No? Okay, don't worry. We can discuss this in the following slide. Why are the transitions element complexes colored? It is due to the electronic transitions within the d orbitals of the metal ion. It can be illustrated more in the following process. When the ligands surround a transition metal ion, they interact with its d orbitals, causing them to split into different energy levels. It is called the crystal field splitting. The extent of this splitting depends on the geometry of the complex, the nature of the ligands, the oxidation state of the metal, and the types of the metal ion. Electrons in the lower energy d orbitals absorb specific wavelengths of visible light and jumped to the higher energy d orbitals. It is called the dd transitions. The absorbed light corresponds to the energy difference between the split d orbitals. The color we see is the complementary color of the absorbed light. For example, if orange light is absorbed, the complex appears blue. In addition to the dd transitions, in some cases, the color arises from the charge transfer transitions. There are two types, the metal to ligands or the ligands to metals charge transfer, which are typically more intense than the dd transitions. There are four factors affecting the color of the complex: the oxidation state of the metal, the nature of the metal ion, the geometry of the complex, and the type of the ligand. For the oxidation states of the metal, the oxidation state of the metals affects the color of its complexes because it influences the d orbital splitting, the energy gap between the split d orbitals. Below are some scenarios to illustrate more detail. The effective nuclear charge. A high oxidation state increases the effective nuclear charge of the metal ion. It pulls the ligands more closer. This also strengthens the ligand field and causes greater splitting of the d orbitals. It alters the wavelengths of light absorbed. Electron configurations. The oxidation state determines the number of d electrons available for the transitions. For examples, a metal in a high oxidation state may have fewer d electrons, which can change the type and intensity of the electronic transitions. For examples, the chromium 3 plus ions, it has the 3d electrons, and the chromium 2 ions has 4d electrons. Charge transfer transitions. High oxidation state can enhance the charge transfer transitions, which often produce intense colors. The ligand interaction. The oxidation state affects how the ligands interact with the metal ions. It results in influencing the overall geometry and the electronic environment of the complex. The second factor is the nature of the metal ion. The nature of the metal in a complex affects its color. It is due to the differences in its electronic structures and the interactions with the ligands. Below are some scenarios. The number of d electrons. Each transition metal has a unique number of d electrons, which determines the possible electronic transitions. For example, the iron 2 and the copper 2 absorb different wavelengths of light, leading to a distinct colors. For example, the iron 2 is green color and the copper 2 is blue color. The nuclear charge. Metals with higher nuclear charges create stronger ligand fields, increasing the splitting of d orbitals. This alters the energy gap and the wavelengths of light absorbed. The spin state. Some metals can form high spin or low spin complexes, depending on the strength of the ligand field. This also changes the energy of the DD transitions and consequently the color. The charge transfer transitions. Certain metals are more likely to exhibit charge transfer transitions. For example, the iron 2 iron, which can dominate the observed color. The third factor is the geometry of the complex. The arrangements of the ligands surrounds the metal ions affects the splitting pattern of the d orbitals. It alters the wavelengths of light absorbed. There are two kinds of the complex. One is the octahedral complex, and another one is the tetrahedral complex. In the tetrahedral complex, the d orbitals split into two different levels, with 3 orbitals at the high energy levels and 2 orbitals at the lower energy level. In the octahedral complex, the d orbitals split differently, with 2 orbitals at the higher energy level and 3 orbitals at the lower energy level. The energy gap between these orbitals in the octahedral complexes is generally larger than that in the tetrahedral complex. It results in altering the wavelengths of the absorbed light and consequently of different colors. The last factor is the type of ligand. The types of ligands significantly affect the color of a coordination complex due to its influence on d orbital splitting and electronic transitions. It is also related to the spectrochemical series, which arrange the ligands in order in the ability to split the d orbitals in the octahedral complex. For the ligand field strength, strong field ligands such as the cyanide and ammonia forces larger splitting of the d orbitals. It will lead to the absorptions of higher energy light or shorter wavelengths. Weak field ligands such as the water and chloride ion results in a smaller splitting of d orbitals, which absorbs the lower energy light or the longer wavelengths of light. For example, it has a water chromium 3 is dark blue, and has ammonium chromium 3 is violet. The charge transfer transitions. The ligands, like the carbon monoxide, can accept the d electrons from the metals, which enhances the metal to ligand charge transfer, which often produce intense colors. While the ligands, like the halides, donate the electrons to the metal, facilitating ligands to metal charge transfer, which also contributes to the colorations. In conclusions, the transitions metal complexes are colored due to the DD transitions and the charge transfer effects. The color depends on the factors such as the oxidation state of the metal, the nature of the metal ions, geometry of the complex, and the ligand's type. These lessons, we have learned the reasons of the transition element complex are colored and the factors affect the color. Now I have one question to the class. Are all transition element complex colored? Anyone know the answers? Anyone can try? No? Okay. Not all the transitions element complex exhibit colors. Can you please explain it with two scenarios and name one transitions metal complex in each scenario? Anyone can try these questions? No? Okay, here is the suggested answer. The scandium and the zinc iron are typically colorless in aqueous solutions because they lack partially filled d electrons, partially filled d orbitals. The scandium has an empty d orbitals, that is no d electrons. It means that there is no possible dd electrons to absorb the visible light. The zinc 2 iron has a completely filled d electrons. There are the 10 d electrons in the electronic configurations. So there are no available energy gaps for the electronic transitions that would result in color. Any questions? Clear? Yes? If you have further questions, don't hesitate to approach me. Okay, if no questions, we can dismiss the lessons. Thank you very much.